Welcome everyone. This is a lecture on numerical differentiation. So what we're going to talk about today are computational schemes that allow us to take data, and normally this is in the form of some kind of vector, right, once we're in the computer, and then how do we produce derivatives of this data. All of this information, the code that I'm going to talk about here, can be found on the course website, which is listed right here, and you can find other lectures and everything else that you need here, including the notes. So a numerical differentiation. Normally what we're thinking about in differentiation is one of the most common things we need to do in the sciences, because almost all of our engineering and physical systems, the language in which we express relationships is around rates of change, whether it's spatially or temporally. We write down governing equations, typically using calculus as the underlying mathematical structure. And so very early on, when we take calculus, we learn this idea of a derivative. And here is the definition of the derivative. It's a very intuitive way to start thinking about things. And calculus is really about understanding infinitesimals. So when we think about this idea of a derivative, what it really means here for us is to take a slope formula. So this is nothing more than rise over run. So I take a function evaluated at t plus delta t minus f of t divided by delta t. And the definition of the derivative is then to take that delta t going to 0. Okay? And really, at the end of the day, what this really means is that I have on top, if I take delta t to 0, this difference goes to 0, and of course the bottom goes to 0. And this is very difficult for a computer to do, obviously, because you're going to get a divide by 0. And what calculus taught us was that if you take 0 divided by 0, we make sense of it because we get some kind of expression that is that makes sense out of this limiting process, which gives us an instantaneous slope of this function, which we call the derivative here. Now what I'm working with here is formulas that are in time, df dt, but we could also think about a function in x, df dx. It doesn't really matter. T and x are just dummy variables. And what we want to do is start thinking about taking functions and producing derivatives, and what are the algorithms that allow us to do this. So that's the definition of the derivative. And what we're really going to do is focus in on here. We're not going to take delta t to 0. We're going to take the delta t to be very small, but not 0. And that's exactly how we're going to actually develop the themes around numerical differentiation. So remember, this is just a rise over run formula, and it just allows us to think about how would we compute this in some kind of practical way. Now the big question you have to ask, of course, is we obviously can compute slopes by rise over run, but it's not enough to say here's an approximation. One of the things that's really important in scientific computing is to be able to not only approximate it, but also tell people here is my error in this approximation. So when I take these rise over run formulas, and what we'll show is we can get some very sophisticated rise over run formulas, and the sophistication is aimed at one thing, which is producing an estimate of the derivative with smaller error. So that's what we're going to go after in here and talk about how to do it. So let's start off with this idea of a Taylor series. So here is a Taylor series. Taylor series is actually one of the most important concepts that we'll be using in all of scientific computing. So you just have to really know what a Taylor series is. So what it is from calculus, what we learned is if I take a function, evaluate t plus delta t, then I can actually evaluate this around f of t. So f of t plus delta t is the function f of t plus delta t, its derivative, plus delta t squared over 2 factorial, its derivative, plus here we're going to cut it off at delta t cubed over 3 factorial. And what we know from calculus is that in fact we can express this as a third derivative with some constant c1. This is an exact expression, and c1 itself belongs somewhere in the interval t to t plus delta t. So it turns out you could search for this c1, but the fact is I don't really care what the c1 is. All I care about is that this thing here is the upper end of what my expression is, and in fact I'm actually going to ignore this term down the road. So this is actually just a very simple expression from Taylor series, and again you should familiarize yourself with Taylor series because they are going to be the basis of almost everything we do in scientific computing, because when we start thinking about calculus-driven models, which is most of physics and science, where we have the relationship between time and space derivatives, because we have derivatives in there, almost all the derivatives we're going to approximate using formulas like this, which are called finite difference formulas. So I could take this expression where f of t plus delta t, or I could do also an expression where I take f of t minus delta t. So I just take this expression above, and wherever I see a t, I replace it by minus t. So for instance, f of t minus delta t, I get a minus delta t here. And then I also get a minus delta t squared cubed here. Okay? So I have these two expressions, and this thing closes off with some constant c2, and c2 is in the interval t minus delta t. So I have these two expressions for how to evaluate f of t plus delta t, f of t minus delta t, and centered around f of t. So at this point, I haven't really done anything. I've just simply said we have these Taylor series expressions. And what we're going to do now is we're going to show how, using these Taylor series expressions, we can generate not only formulas for how to approximate derivatives, but also error estimates from using these formulas. So let's come back to these two expressions. Here they are. And what I'm going to do with these two expressions is I'm going to take the second formula here, and I'm going to subtract it all from the top formula. So, okay, so take this equation, subtract this equation, and ask, what do I get in the subtraction process? So first of all, on the left side, you get these two terms. But notice when I subtract, these terms are going to drop out because they're the same. I'm subtracting. And these two terms are going to drop out. So that's very nice, because what you're ending up with is the following expression. What it's telling you here is I get the difference, f of t plus delta t, minus f of t minus delta t. And then on the other side, I get 2 delta t, the derivative df dt, and then some expression involving these third derivatives that I have here. Okay? So what I'm going to do now is actually, from this expression that I get from subtracting, I'm going to solve for the derivative term df dt itself. And in doing so, here's what you find. You move everything over to the other side, and you find df dt is the difference between f of t plus delta t, f of t minus delta t, over 2 delta t. And then you get this expression here, which what I've done here is I've used an average of those third derivative terms. Now it turns out I'm not going to care about this term so much. Mostly I want to focus in on this term here. And what does this term tell us? Essentially what this term tells us is an expression for the rise over the run. You're using two neighboring points, f of t plus delta t and f of t minus delta t, and the difference between them is 2 delta t, so it's the rise over the run, which of course we already know is the way to start thinking about derivatives, is just a slope formula. But now what we have here by doing this Taylor expansion is we also have this error term at the end here, and that error term is telling us there's a delta t cubed plus that third derivative. And so it tells us when I do this expression, I also have this I have to think about, and then what do I do with that? Well, what we're going to do with it is ignore it. Mostly what we care about that error term is in front of that term is a delta t squared. So that is going to be our truncation error. If I decide to ignore this term and not evaluate it, how much error am I making? Well, I don't know exactly the number, but I know it scales like delta t to the cubed squared term. So this is a second order accurate scheme. The second order refers to the fact that it's delta t squared. Okay, so if I take a delta t that's 10 to the minus 2, my error will be 10 to the minus 4. So now I've given you something very important here. These formulas tell you not only how to represent the derivative, which is a slope formula, but in representing it, how does the error scale? And here the error scales like delta t squared. Okay? So, you know, just to draw this and to be more specific, I want to just think about what we're really doing here. If we have some function, here's some function that I have, right? And remember, functions don't really exist in MATLAB. What they are is a finite number of points. And let's say these are my points that I actually have to represent that function, right? So everything in the computer is a representation in terms of a finite number of points because it's either a vector or a matrix, okay? And then I could ask the question, if I want to compute the derivative, let's say at this point right here, how would I do it? What this formula tells me is to say I need to use the 2 points near it. So in other words, if I look at this point, I want to use this as the point in front. That's the f of t plus delta t. And then use the point behind, which is f of t minus delta t. And the run here is 2 delta t. So essentially what I'm doing is in drawing a curve which goes through the 2 neighboring points to approximate the derivative. That's what the slope formula tells us. So it's just, there is nothing here I'm telling you that's new that we didn't know in calculus. It's just we knew in calculus that the derivative was a slope, and what I've done here is derive this slope formula, not by using just 1 point, but using 2 neighboring points, and in using the Taylor series expansion, I also told you what the error was in using these points. When you do calculus, you actually take delta t to 0. And so we don't think about a truncation error, right? You normally in calculus are actually trying to find closed-formed expressions as delta t actually goes to 0. Here, by making delta t small and not 0, I have to think about how do I approximate it, and not only how do I approximate it, which is here, but what is the error in this approximation that I have. Okay, so that's the concept. It's hopefully very intuitive, and what we're going to do is now build on that to start thinking about how to make more accurate schemes and how to use these methods in a very nice way. By the way, one other thing I have to point out, if I have a function here, is if in fact I have an endpoint, here's the endpoint over here, so the question is, what is the derivative around that endpoint? Notice that this endpoint over here has no neighbor on this side, on the far side of it, okay? So it has no f of t plus delta t. It has, however, a neighbor on this side, and so it can use that. So how would I compute the derivative there? In that case, I still want to use my neighbors, but it turns out I can't use the neighbor that's on the far side of it because I only have neighbors on this side. So in that case, you're going to use what's called a backward difference formula. You're going to take that point and you're going to use the points that are on the other side of it, and you're going to use these Taylor expansion ideas to construct an approximation of the derivative. Same thing happens if you're trying to do a derivative on this side over here. If you're here, it only has neighbors that into the interior of the region. It has no neighbors on this side. So you would use just neighbors there, which is a forward difference formula. So all the concepts hold. All we're going to do, though, is when we derive these formulas, is we want to compute these slope formulas and also provide an error assessment when we do it. Okay, so it's not just enough to just compute a slope. You have to compute a slope and have an approximation to the error. Okay, that's really important scientific computing, is to understand your error as you build out your code to do approximations. Okay, so let's start off with this process. So we've already shown you that if I just take 2 Taylor series and I add and subtract it, I could get this nice representation by using 2 neighbors of an second order accurate finite difference scheme. I'm going to show you one other thing that we can do here. How would we get more accurate schemes? So that's something that people are very interested in, is they would like to use derivative formulas to get as accurate of the derivative computation as they can. So we're going to look at here is saying, well, now let's use the same things that we did before. I'm going to use an expression here for f of t plus delta t, but notice I'm going to expand it, and before I stopped the expansion at the 3rd derivative, but now I'm going to go all the way to the 5th derivative before, in fact, I truncate. So I have a 5th derivative evaluated at some c1, which that c1 is some value between t and t plus delta t. So this is just standard Taylor series expansion and Taylor's theorem. And I'm also going to take f of t minus delta t, and all I have to do is replace from the top formula, wherever it says t, replace it by minus delta t. Here's the expansion, and again, I'm going to have here now up to the 5th derivative. So now what I'm going to do is do exactly what we did before, just simply take the second equation here, subtract it from the first, and what you're ending up with is this expression here. But now what this expression gives you is you're going to get the difference of the points, f of t plus delta t minus f of t minus delta t. And now you're going to get an expression of the derivative, but now what didn't go away this time is the third derivative, and then you have a fifth derivative. So what I'd really like to do is I'd like to get rid of this third derivative term. So the trick in all this Taylor series expansion methods is that, how about if I find another way, do another expansion so that I can try to remove this term here, because if I can remove this term here, what this has in front of it is delta t to the fifth. And so my error is going to be pushed way smaller if I can just get rid of this. And the way we're going to do this is by doing this expansion again. So here's the expansion we have that we just showed. But now we could do the same expansion. Instead of around f of t plus delta t, we could do f of t plus 2 delta t. In other words, use not the immediate neighbor, use the neighbor that's 2 delta t away, and 2 minus t minus 2 delta t, okay? So we could do Taylor expansions around that as well to get a second expression. And this is the second expression, so now I'm using 2 neighbors over on either side, and it's just essentially this formula, but where I see t, delta t, I replace it by 2 delta t, okay? And when you do that, here's the expression you get. So now we have f of t plus 2 delta t, f of t minus 2 delta t. You now get 4 delta t here, 16 delta t cubed here, and you get these terms here. So now that I have these two expressions, guess what I'm going to do? I'm going to take these two equations, the top one and the bottom one, and find a way to basically add or subtract them together so that I can do one thing, which is remove the third derivative term, okay? And so when you do that, you're going to have to basically say, well, if I subtract these, notice I have 16 delta t cubed here and just a 2 delta t cubed there. So if I multiply the top equation by 8 and then subtract it, these two terms will drop out. So that's the whole idea behind using these Taylor series, and not just using your neighbors, but now you can use your neighbors' neighbors. In fact, the more neighbors you use, you can construct more and more accurate numerical schemes using what's called the finite difference schemes. And this is what this is. So if I do that, subtract it, here is, in fact, the formula that I have for the derivative. So what I have here is df dt, so that's the derivative formula. And now what I have is minus f of t plus 2 delta t, 8 of t plus delta t minus 8. And remember, the 8 comes from the fact that I had to multiply this equation by 8. So what I use is my neighbor 2 over, 8 of the next neighbor, 8 of my other neighbor, and just my neighbor 2 over again, divided by now 12 delta t. So this is what's called a, now I'm using 2 neighbors, and this is a 4th order accurate scheme because look at the error. Once I get rid of the third derivatives and drop them out, then here, notice I have a delta t to the 4th. And so I'm not going to care so much about how big this term is. All I care about is now delta t to the 4th. So if my step delta t is 10 to the minus 2, then you take 10 to the minus 2 to the 4th power. My accuracy is 10 to the minus 8. So this is quite remarkable. Just by using not your 2 nearest neighbors, but your 2 nearest neighbors and their neighbors, I can drop my accuracy considerably all the way down to t to the 4th power. Okay? So that is the idea behind using Taylor series. And in fact, you could imagine if I use more neighbors and do a higher expansion, I could generate order delta t to the 6th accurate schemes or delta t to the 8th accurate schemes. And mostly what this involves when you do Taylor series is just use more neighbors to approximate that derivative. So that's the main idea behind using Taylor series for approximating derivatives. And this is very commonly done because we need to often approximate derivatives in time, derivatives in space, and this is the sort of the standard way to do it. One comment before we go on is that if you have noisy data, if it's real data and it's noisy, often these finite difference formulas are not very good. Okay, and we have more sophisticated methods for producing derivatives. But when you're doing computation, scientific computing, oftentimes the derivatives are, you're actually simulating a system and you have nice clean data that you're simulating, and these formulas actually work quite nicely for you. Okay, by the way, I should also point out, Notice that what we did here to approximate the derivative, we took the Taylor series expansion from f of t plus delta t, and we subtracted the Taylor series expansion from f of t minus delta t. If instead I would have added those two series, I can actually produce an approximation for the second derivative. And here's what you would get. The second derivative is your neighbor in front, t plus delta t, minus twice your current value, f of t, plus your neighbor 1 back, f of t minus delta t, all over delta t squared. So this here, you can play these games not only to produce more and more accurate derivatives, but you can also play these games to produce estimates for higher derivatives, including second derivative, third derivative, fourth derivative. Okay? So this is all based upon Taylor series expansions. And of course, Taylor series are not that difficult to work with. You just have to do a lot of algebra to work out these expressions. And you also get yourself out what the error is when you approximate these things by these expressions. All right, so in the notes that are available at the website, you can download these. I have some tables, and these tables become important because the tables are what are really you're going to use in practice to start programming up derivative estimates for different functions that you might want to work with. So for instance, a table has order delta t squared accurate. These are center difference schemes. In other words, center difference means I use my neighbors on both sides of me. And these center difference schemes, so for instance, the one we derived initially here was the first derivative is the point in front minus point behind divided by 2 delta t. But what I also have there is an expression for how to compute the second derivative, the third derivative, the fourth derivative. So you can do all of these derivatives very nicely just by using these formulas right here. And all of these formulas are delta t squared accurate. You can even make it more accurate by doing fourth order accurate schemes. And what you really do when you move from second order to fourth order accurate, you use more neighbors. So for instance, the first derivative formula, which is this first one here, it's the fourth order accurate scheme. Instead of just using your two neighbors, use the two neighbors, one on each side, use two neighbors on each side. So you have 4 neighbors that you use in total. And that is how you actually drop the accuracy down to delta t to the fourth from delta t squared. Oftentimes in practice, people will always use at least delta t to the fourth. It's just such an improvement in accuracy. And that's something that you want to be aware of. How much extra work do I do to get this much accuracy? And the answer is not that much extra work will actually get you quite a bit more accurate solutions. And so oftentimes people use a higher accuracy scheme. You know, delta t to the 6th is very high accuracy, but delta t to the 4th, super easy to use, and it's kind of a go-to oftentimes in practical schemes. Delta t squared is kind of, you know, for very little extra work, you can get the error better, so you should just do it. Finally, one other set of schemes right here. These are ordered delta t squared accurate forward and backward difference formulas for both the first and second derivative. These formulas are really important at the boundaries. So when you're at the edge of the domain on one side or on the other, where there's no neighbors on either side, you cannot use these center difference formulas that are represented by these two schemes here. So you have to start using just the interior points, and these formulas here, these forward and backward difference formulas, are the formulas that you would use right there to start computing the derivatives across the domain with center difference, and on the ends you use this forward and backward difference formulas, and that allows you to use just the interior neighbors because you have no neighbors on one side of you. So these tables are important in practice, and so you can see them in the notes, and you have them available to you to be able to produce derivative estimates very nicely. Okay, one of the things that's we should talk about before really finishing up is this idea of, at this point it looks like all I have to do to get better error is just take delta t to be smaller and smaller and smaller. But in fact, there's this really interesting issue that comes up, which is having to do with numerical round off. In computation, typically what we're working with is double precision numbers that actually go down to 16 decimal place precision. Okay? And so at that point, the question you can ask is, what's the impact of having that numerical round off down there on actual computation. So I want to investigate that and show that in fact below a certain step size you are not in fact becoming more accurate. In fact, you do much worse because of numerical round off. So the idea is that anytime you actually represent any kind of number in MATLAB or Python as some kind of numerical scheme up to 16 decimal place accuracy, there is a round off error that occurs there. This is just a representation of that round off error. That's E. Okay? So not only do I get a round off error for the point y of t plus delta t, I get a round off error for y of t minus delta t. So let's call these here. And so what we're going to investigate next is what is the impact of that on my actual numerical scheme. So when I try to compute the derivative itself, my derivative formula is, the actual numerical representation of the solution in the point in front, point behind over 2 delta t. And then I have some error here. Now the error now is going to be composed of two pieces, both the round off from the fact that I did a Taylor series expansion, but also the numerical round off I have right here. So when I look at this and I say my error is composed of these two components, the truncation from the Taylor series and numerical round off, this is what it looks like. So here's my numerical round off. This comes from just when I evaluate those expressions in practice, they're only accurate to 16 decimal places. But also I have this term that I've neglected, which is the third derivative with some c. So the question is, what's the impact of this error, which is typically really small, on my step size? And in fact, you can just say, let's try to bound this error. So if I say my numerical round off is bounded by some number, and typically this number is around 10 to the minus 16, 10 to the minus 15. So let's just make 10 to the minus 15 as a nice number. It's just a little bit around where the numerical round off floor is. And then we could say if the third derivative is bounded by some maximum value m, then what I can do is say my error then is bounded by the following expression. Here's my numerical round off. Here is the biggest value of my third derivative. So then I have this expression right here for the error, or the maximum error. Now notice one really important piece here. On the bottom of this, you have this e to the r divided by delta t. So as delta t goes to 0, this term here blows up. This term here appears due to numerical round off, whereas this term here goes like delta t squared. So as delta t goes to 0, then this term gets smaller and smaller. Okay? So what this means for you is that if you were to actually try to minimize the error, then you would just take the derivative of this, set it to 0, here's the derivative, and what you find is that in fact, by the way, here's the two curves. The one curve, the delta t squared, goes like this, the 1 over delta t goes like this. This one here is from the numerical round off. This one here is from the third derivative. So your error is this solid curve here. And notice the error grows as you take delta t big. It's smaller and smaller, and then eventually it blows up here. It goes to infinity because you're dividing by 0. And the question is, the minimum error is here, and I get that by basically taking the derivative. And you can find it's given something like here. Okay? So there it is. Now notice this is 3 e to the r, which is this numerical round off, over m, which is the maximum third derivative, to the 1/3. So if e to the r is like 10 to the minus 15, I take this 10 to the minus 15 to the 1/3 power. This is like 10 to the minus 5. What we're really saying then is your delta t here, which is the minimum step size for the minimum error, you shouldn't take your delta t any smaller than 10 to the minus 5. Okay? Because once you take it smaller than 10 to the minus 5, what's actually happening due to numerical round off, your error is actually getting bigger. Okay? So this is really important when you're doing finite difference schemes or these Taylor expansion schemes, because numerical round off can play a role if you push that delta t to be too small. Notice that in calculus, we're always trying to take delta t as small as possible, right? That's the idea of a definition of a derivative. Take that t, take it to 0, and what this is saying, because you have finite representations in the computer, that you only have 10 to the minus 6 accuracy, that in fact you should not take it beyond 10 to the minus 5th for this second order formula, because in fact you'll start making errors and it's all due to this numerical representation issue. So something important to keep in mind. All right, let's get to some coding and just walk through a little bit of code. Here's some MATLAB and Python code, and all these do is a second order finite difference scheme for computing the derivatives. So in Python, what you have here is I'm going to take a function, we're going to differentiate sine, and we already know that the answer is cosine. By the way, this code you can download off of the website and play around with it. I have some plotting options there so you can actually look at what these things look like. But basically what we're going to do is say, let's take a dx of 0.01, okay? And so we're going to do NPA range from -4 to 4 and take steps of dx. And we're going to basically take the sine function to differentiate. Y prime exact is cosine. So this is what this expression is. This is the actual answer right here. So after we differentiate this, we can always actually plot our differentiated answer and compare it to the cosine and see how well we did. After all, we've taken dx of 0.01, so 10 to the minus 2. What we expect, since this is a second order scheme, is that we would be accurate to 10 to the minus 4. And in fact, if you plot the exact solution and your approximation and you zoom in, you'll see that's about right. You'll see that your approximation starts to fall off the real value down in 4 or 5 decimal places. Okay, so how do you do this? Well, I'm going to take this domain. I have the first point and the last point don't have neighbors, so I have to use a forward or backward difference formula. So first thing I do is create a YP, which is my Y prime estimate. And first in Python, since I don't have dynamic allocation of the vector, I just make it a bunch of zeros. And then the first thing I do is first I use a formula to compute. This is a forward difference formula computing the derivative at the first point, y0. And I use the formula right out of the tables, which is -3 of the point I'm at, plus 4 of the point in front of me, minus 1 of the point y of 2. And then divide by 2 of x. The last point has a backward difference formula, which is yp of n minus 1 is actually the opposite values of the signs here. It's 3 of the current point minus 4 of the point interior, and then plus the point 2 points away from you divided 2 delta x. Those are the endpoints. I'm using the forward and backward difference formulas from the tables. And then in the rest of it, I just use my neighbors. So for j equals in range 1 to n minus 1, these are all the interior points, and I just use point in front, point behind, divided by 2 delta x. That's it. That's how you differentiate this thing. Slope formulas all the way through, and at the endpoints, you just use a forward and backward difference formula. You do the same thing in MATLAB here. You can basically take this thing, divide it up, break it up into a domain, 0.01, take the sine, here's the actual cosine, and you can say, here's your first point, you just use your forward difference formulas. In the interior, point in front minus point behind divided 2 delta x. And then finally at the end, you just use your backward difference formula. So when you're over there at the end, you just use the points in front of it. And that's it. That is all you need to start building a little approximation for derivatives. Okay? So with these formulas, the idea is that you actually have the ability now to take some vector, which represents some quantity of interest. For instance, if I give you a vector of velocity, a vector over time, so that velocity vector, if you want to find the acceleration, you could apply this formula here, and you can actually compute the acceleration because that is the derivative of that velocity vector. And this is one way to approximate that in practice. All right, so that's kind of the main ideas behind numerical differentiation. Use Taylor series expansions, and what it does is you use your neighbors to compute slope formulas. And in fact, if you use more neighbors, you can compute a very sophisticated slope formula that gives you even better accuracy. All the tables are on inside of the notes, and so I encourage you to look those up and have those handy because we use them all the time for computing derivatives, which are the basis of doing almost all of our physics and engineering science efforts.